Welcome to section 6. Until now, we have created independent classes for our components. But what if we want to create a more advanced version of an existing class? In this section, we will learn about inheritance, a core OOP pillar that allows us to create an LED blinker by extending our original LED class. Inheritance creates and is a relationship. An LED blinker is an LED, but with extra features. Instead of writing the code to control the hardware pins, our new class will inherit those abilities from the original LED class. This promotes code reuse and keeps our project organized. In C++, we call the original class the base class and the new one the derived class. As you can see, the LED blinker will have everything the LED has, plus new attributes like interval and previous millis to handle timing without blocking the execution. We won't just use the LED methods, we will override them. For example, when we call on a blinker, it needs to start the blinking timer, not just turn the light on. We will also add a setrate method to change speed, and an optic method to keep the timing engine running. Inheritance is a game changer for scaling your Arduino projects. Let's start building it. In the next lecture, 06.02, we will create the LED blinker class structure and learn how to initialize the parent class. See you there. It is time to get our hands dirty with code. In this lecture, we will create the shell of our LED blinker class and learn a crucial C++ technique, how to initialize a parent class from a child class. This ensures our hardware is set up correctly before we add our custom blinking logic. In our header file, we use the colon syntax followed by the public keyword and the name of our base class, LED. This tells the compiler that LED blinker inherits everything from LED. Inside, we add our new private variables for timing and state tracking. This part is very important. In the constructor, we use a member initializer list that is the colon followed by the parent class name LED. We pass the pin argument directly to the parent. This is necessary because the parent LED class needs that pin to set the pin mode and initial state. By delegating the hardware setup to the base class, we avoid code duplication. The base class handles the pins, while the derived class focuses solely on initializing the timing variables for its new features. Our structure is ready, and the parent is initialized. Now, we need to decide how our blinker reacts when we try to turn it on or off. Coming up next in lecture 06.03, we will learn how to toggle the LED state from within the LED blinker class. See you there. In this lecture, we will implement the control methods for our LED blinker. Because we are using inheritance, we need to decide how the on, off, and toggle methods should behave. We aren't just turning a pin high or low anymore, we are managing the blinking state of our object. When we call on, we want the LED to start blinking. So, we set his blinking to true and then call the parent on method from the LED class to physically turn the light on. Conversely, off sets his blinking to false and calls the parent off method. To override, you need to put virtual keyword like this. in front of the method you want to override in base class. Next, you need to put an override keyword in back of method like this. The turtle method now manages the blinking behavior rather than just the pin state. If the LED is currently blinking, call in turtle will turn it off. If it is not blinking, it will call our new on method to start the blinking sequence. In turtle method definition for LED class, you must add LED : at these two positions. That means you tell the program you need to implement on method of LED class and off method of LED class, not anything else. By using the LED : syntax, we tell the compiler to use the original hardware logic from our base class. This allows us to add our blinking logic on top of the existing hardware control without rewriting the pin management code. We have the controls in place, but our LED isn't actually blinking yet. In the next lecture, 06.04, we will implement the non-blocking timing logic inside the update method to bring our blinker to life. See you there. In this lecture, we are going to implement the heart of our LedBlinker class, the update method. This is where we make the LED blink without using the delay function, allowing our Arduino to handle multiple tasks at the same time. This is the ultimate goal of creating a specialized blinker class. The logic follows the blink without delay pattern. We check if the difference between the current time and the last time we turtled the LED is greater than or equal to our defined interval. If it is time to switch the LED state and update our timestamp. Inside LedBlinker.cpp, we define the update method. First, we check there's blinking flag. If it is false, we return immediately to save processing power. If it is true, we perform our timing check using millis. When the interval expires, we call the parent's turtle method to change the light state. To make this work, you must call the update method inside the main Arduino loop. Because our logic is non-blocking, the loop can run thousands of times per second, and our LED objects will only turtle precisely when their individual intervals are reached. By putting the timing logic inside the class, we've created a component that is clean. It manages its own time and state, leaving your main program free to handle user inputs or senses without more mess. Our blinker is now fully functional. But what if we want to change the blinking speed while the program is running? In the next lecture, 06.05, we will add getters and setters to control our objects dynamically. See you there. Now that our LED blinker is working, we need a way to interact with its internal settings safely. In this lecture, we will implement getters and setters. These methods allow us to modify the blinking interval or check the current status of the object from outside the class while keeping our data protected. In OOP, we keep attributes private to prevent external code from accidentally breaking our logic. For example, we don't want another part of the program to set a negative interval. By using a setter method, we can control how the interval is updated and ensure it remains valid. You can get the data of attributes with another type of returning value by using getters. We will focus on the setRate method. This method takes an unsigned long as an argument and assigns it to our private interval variable. This allows us to change the blinking speed dynamically, perhaps based on a sensor reading or a user command, without needing to recreate the object. Here, I don't change anything, just return its original value. In the header file, we ensure setRate and getRate are listed under the public section. This makes them part of our class interface. Other developers, or even your future self, can now see exactly how to interact with the timing of the blinker without needing to understand the internal millis logic. This pattern is called encapsulation. It makes your code more robust because it creates a clear boundary between how the object works and how you use it. You can change the internal implementation later, and as long as the setter name stays the same, your main program won't break. We have built a fully customizable, intelligent LED component. Now it is time to see it in action at scale. In the next lecture, 06.06, we will create an application example where we make 3 different LEDs blink at 3 different rates simultaneously. See you there! In this final lecture of the section, we are going to see our hard work pay off. We will use the LedBlinker class to create 3 different objects, each controlling a physical LED at a completely different rate. You will see how easy it is to scale your project once you have a solid class structure. First, we include our LedBlinker header. Then, we instantiate 3 objects, red, yellow, and green. We assign them to pins 12, 11, and 10. In setup, we use our setter method, setRate, to give each LED a unique speed, 100 milliseconds for fast, 500 for medium, and 1 second for slow. Look at the loop function. All we need to do is call the update method for each object. We don't need any complex global variables or nested if statements here. Each object independently tracks its own time and state, ensuring they all blink at their designated rates without blocking each other. By using inheritance and the update pattern, we've moved the complexity out of the main sketch and into the class. This makes our code much easier to read and maintain. If you wanted to add 10 more LEDs, you would simply follow the same pattern without making the loop any more complicated. You've mastered the LedBlinker and the power of inheritance. Now it is time to face the final challenge of this course. In the next section, we will build a complete traffic light system. Coming up in lecture 07.01, we'll dive into the final project overview. I will see you there.